Welcome to this explainer. I'm really thrilled you're here today because we're looking at a massive, urgent shift happening right beneath our digital feet. Every time you ask an AI a question or stream a 4K movie or process big data, you're generating heat, a lot of heat. For decades, the backbone of the internet has basically relied on traditional air conditioning to keep servers from melting down. But that era, well, it's rapidly coming to an end. So let's dive right in and demystify why modern data centers are making this inevitable shift from air to liquid cooling.
Let's start with a number, 700 watts. That is how much power a single, recent, high-end GPU can consume all by itself. I mean, just a few years ago, we were worried about CPUs that generated maybe 200 or 300 watts. Now, with the absolute explosion of AI and advanced processing, we're looking at silicon that runs incredibly hot. Just imagine a standard server rack packed with these things. A modern system with just 2 CPUs and 8 of these high-performance GPUs requires about 7 kilowatts of cooling capacity. That is a staggering amount of thermal energy. We're literally reaching a physical limit where you simply cannot blow enough cold air over these chips fast enough to stop them from catching fire.
For years, we've relied on a remarkably simple mechanism. You pull cool air in from the front, a fan forces it over the hot CPUs and GPUs, and it blows out the back as hot air. The cooling ability here is entirely dependent on how cold that inlet air is and, of course, how powerful your fans are. But here's the fundamental problem. There's a dimensional limit to how large a fan can actually be inside a server chassis. You can only move so many cubic feet of air per minute. When you have a rack demanding 7 kilowatts of cooling, those fans have to spin at hurricane speeds, consuming massive amounts of electricity themselves, literally just to keep up.
So what happens when those fans inevitably fail to keep up? Well, you get what the industry calls jitter. And this is the real-world consequence of all this heat. Jitter isn't just a slight delay, it's thermal throttling. When your CPUs or GPUs get dangerously close to their maximum operating temperature, the hardware goes into survival mode. It will literally throttle back its own performance, reduce its clock rate, or even shut down processing cores entirely just to prevent physical damage to the chip. For a data center running, say, critical AI workloads or high-frequency trading, jitter is the ultimate enemy. It absolutely kills application throughput and destroys the processing speed you just paid millions of dollars to achieve. The fundamental solution to this bottleneck comes down to basic physics. We simply need a better medium to capture and carry away heat. Think about air for a second. It's a gas. Its molecules are widely spaced apart. And because they're so far apart, air is frankly terrible at absorbing heat efficiently. Now contrast that with liquid. Liquid molecules are densely packed together. This simple physical difference means that liquid has a drastically higher heat transfer rate. When a hot surface touches a liquid, those tightly packed molecules can absorb and carry away the thermal energy at a rate that air could never even dream of matching.
And we aren't just talking about minor, incremental improvements here. These are orders of magnitude. Listen to this. Water has 1,000 times more cooling capacity than air. 1,000 times. Furthermore, because it holds so much thermal energy, it requires 10 times less transport energy to actually move that heat away from the source. And when you look at the thermal conductivity, actually pulling the heat out of the chip, water is 25 times better. This is exactly why future generations of hardware won't just benefit from liquid cooling, they're going to absolutely require it. Air cooling has simply hit a brick wall.
So how do we actually apply this in a real server? Enter direct-to-chip, or D2C technology. Instead of a massive, super loud fan sitting on top of your processor, you have a sleek, contained cold plate sitting directly on the running chip. There's a thermal transfer material right between the silicon and this copper plate. A dedicated micropump circulates cold liquid constantly over the top of the plate. The liquid absorbs that massive 700-watt heat output instantly and carries it away in a totally sealed, contained loop. It's quiet, it's remarkably efficient, and it completely eliminates the need for massive airflow over the motherboard. Now, once that liquid absorbs the heat from the chip, where does it actually go? Well, if you follow the flow, the hot liquid cycles out of the server rack and flows into what's called a cooling distribution unit, or a CDU. Inside the CDU, the heat is transferred through a liquid-to-liquid heat exchanger. The now cooled primary liquid is then pumped right back to the chips to do it all over again. Meanwhile, the secondary liquid loop takes that transferred heat entirely outside the building, often to a cooling tower. Modern CDUs can remove up to 80 kilowatts of heat from a single rack, which perfectly sustains those high-density AI servers. But what if you need even more cooling? Or what if you don't even have a traditional data center? This brings us to the extreme end of the spectrum, immersion cooling. I know, it sounds a bit like science fiction, but it's happening right now. Instead of putting a cold plate on a chip, you take the entire server, motherboard, memory, processors, the whole shebang, and you completely submerge it in a tank of liquid. Now don't worry, this isn't tap water. This is a highly engineered, non-conductive, non-corrosive liquid designed specifically for electronics. The heat from the components naturally warms the liquid, making it rise, where it's then pumped out, refrigerated, and returned. This provides literally the most extreme heat removal possible and allows for incredibly dense computing in confined, non-traditional spaces.
As an IT manager, you don't just guess which technology to use, right? You engineer it based on your thermal math. If your entire server rack generates up to 25 kilowatts of heat, you can still probably get away with heavily optimized air cooling. But once you cross that threshold into the 20 to 45 kilowatt range, which is exactly where modern AI systems live, direct-to-chip cooling becomes the ideal, highly efficient choice. And when you start pushing past 40 or 45 kilowatts per rack, or if you're deploying heavy compute in a really tight edge computing location, immersion cooling becomes the necessary standard. You simply match the liquid architecture directly to the heat load. Now I know what some of you might be wondering. Installing liquid plumbing sounds expensive, right? Well, let's look at the financial reality. By removing those massive energy-hungry fans and reducing the burden on facility air conditioners, your power usage effectiveness, or PUE, drops from a bloated 1.5 to a hyper-efficient 1.1. In real dollars, even factoring in the estimated $30,000 upfront cost to implement liquid cooling, the energy savings are so massive that a single rack saves over $60,000 over just 3 years. It essentially pays for itself in less than a year, and then becomes a massive profit generator by slashing those operating expenses.
So this isn't just an engineering win. It's a monumental business and environmental win. By switching to liquid cooling, data centers are actually reducing their operational expenditures by more than 40%. But beyond the spreadsheet, this directly translates to massive environmental ROI. By ditching heavy, brute force air conditioning and eliminating thousands of high-speed system fans, data centers draw drastically less electricity from the grid, and that means a direct, measurable reduction in fossil fuel reliance and a huge drop in carbon emissions. Corporate responsibility and high-performance computing are finally aligning perfectly, all through the physics of water.
We always talk about the cloud, like it's this invisible, ethereal thing just floating up in the sky. But the reality? The cloud is heavy, it is incredibly hot, and it relies entirely on physical infrastructure. As artificial intelligence pushes processing to absolute limits we've never seen before, we have to completely rethink how we build the digital world. So I'll leave you with this to ponder. As we submerge our servers to keep them from melting, will the cloud of the future actually be underwater? Thanks for joining me on this explainer, and I absolutely cannot wait to dive into our next topic with you. Keep learning, keep questioning, and I'll see you next time.